All right, well, good morning, and welcome to part 3 of Statistics for Trauma Research. Today we're going to be talking about probabilities and different types of distributions. Previously on Statistics for Trauma Research, we talked about prevalence versus incidence, prevalence being existing disease, incidence being new cases of disease. Incidence is important for being able to study causes of disease. Prevalence is more relevant to the burden of disease. And they are related to each other in that prevalence is equal to the incidence times the duration of disease, so how long it lasts. We also talked about different ways to compare different groups using attributable risk versus relative risk, or the odds ratio. But this time, we're going to talk more about probability, and as it pertains to actual statistical inference. Talk about the concepts of at random and equally likely, and look at a couple different distributions, specifically the binomial distribution and the normal distribution. And then I'll talk a little bit about the central limit theorem and what that implies. So probability is just the likelihood that an event is going to occur. Everybody, when they talk about probability in any statistics class, talks about the jar of marbles or something to that effect. You've got a jar of 100 marbles, 30 of them are blue. What's the probability that if you just reach into that jar and pick out a marble, one of them is going to be blue? And that probability is just 30 divided by 100, or 30%. So the basics, the very, very basics of probability, again, just the likelihood that an outcome is going to happen. Probability ranges from 0 to 1. 0 is it's absolutely not going to happen. 1 is it absolutely is going to happen. And it's calculated just as the number with the outcome divided by the total number in your sample. And here's just some examples. So here's our probability line going from 0 to 1. Some examples. At 0, Padres winning the World Series this year. Snakebite is very, very close to that. Moving up, the probability of somebody visiting an emergency department is actually about 17.6%. Chargers winning the Super Bowl over the next 10 years at least once, assuming a whole lot of other things happen, is about 27%. So stick around, it could happen. Coin flip coming up heads is 0.5. Somebody going to any doctor for a visit within the course of a year, it's actually 82% of people actually go to visit the doctor in a year, and eventually death gets up here to 1. It's definitely going to happen at some point. So just some examples. Let's say we have a population of 5,290 children, ranging in age from 5 to 10, and we want to know what the probability is of somebody being selected. Of course, if you're just talking about one particular child, the probability of that kid being selected is just 1 divided by 5,290. If you want to know what's the probability that a boy is going to be selected, well, then you just take the number of boys, 2,560, divided by that total population of kids. So in this case, it works out to about 48.4%. Probability of selecting a boy who is 10 years old, again, just look at, okay, boys 10 years old, there's 418 of those, again, divided by that total sample size, and you get the idea. Selecting a child who is at least 8 years of age, well, here's where we get to add some stuff up. So we get all of these 8 years old and the 9 years old and the 10 years old. Add those all together, dividing by that total, and about half the kids are in that age range. Now, conditional probability is the probability of an outcome in a specific subpopulation. So if we want to say the probability of selecting a 9-year-old, assuming that person is a girl, then our denominator now is the total number of girls, 2,730. And the numerator is going to be the 9-year-old girls. Probability of selecting a boy, assuming that person is 6 years old, then we start with the 6-year-olds, 892. That's our denominator. And probability of selecting a boy is just going to be the number of boys in that age group. There are a couple of different conditions of probability. One is mutual exclusivity, so mutually exclusive events. The other is conditionally dependent events. Mutually exclusive means that if one happens, the other one is not going to happen. So like a coin flip, it's either going to be heads or it's going to be tails, but it can't be both at the same time. Roll of a single die, it's going to be one of those numbers 1 through 6. More germane to healthcare, the day of week that a patient arrives, you can't have more than one. Mechanism of injury, mostly, although if you watch action movies, of course, the hero can get shot, stabbed, and crash a car. But usually we classify them as either a fall or a motor vehicle or motorcycle or assault or something like that. Gender, again, mostly is only one. So there's an additive rule among mutually exclusive events. And that says that if we want to know the probability of having one outcome or the other, you can just add those probabilities together. So in this case, we had 4.2% of our patients got injured on a motorcycle. 15.9% were injured as a motor vehicle occupant. That is, they were riding in a car or a truck or a van. Of course, there's no overlap in those, so you don't get any of these yes and yes in here, but 80% of our patients were neither of those. So if assuming those are mutually exclusive, the probability of X or Y, motorcyclist or motor vehicle occupant, is just the probability of X plus probability of Y. So if we want to know the proportion of patients that were either motor vehicle occupants or motorcyclists, we just add these up, 4.2% plus 15.9%, and get 20.1% of our patients fell into one of those categories. Now, conditionally dependent is where the outcome of one variable depends on the other variable, or vice versa. So like alcohol results in the time of day, what we will see here. If you're on call between midnight and 4 a.m., you're going to see a lot more alcohol patients than if you're here between 8 a.m. and noon, for example. Survival in GCS, of course, poor GCS, you've got poor survival. Patient's gender and the mechanism of injury, there's a big relationship there. So this is looking at the alcohol results, alcohol test results by the time of day that the patient arrives. And you can see midnight to 3:59 a.m., nearly 60% of our patients tested positive for alcohol. Going down to 8 to noon, it's more like 10%. And you can see how that all shakes out there. So there's a conditional probability going on there. With this is where we have a multiplicative law. So if those two variables, if alcohol and time of day, are conditionally probable, then the probability of both of those happening together is the probability of X, probability of alcohol, times the probability of time of day given alcohol. I should probably phrase that the other way. So probability of time of day times the probability of alcohol given that time of day. So if we want to know what proportion of patients arrived between midnight and 3:59 a.m. and had a positive alcohol screen, then we can look at the proportion who actually arrived in that time frame, 18.5%, and the proportion of those who arrived in that time frame and had a positive alcohol screen, 59.2%. And if we want to know what proportion of our total patients arrived in that period of time and had a positive alcohol screen, we just multiply these two together to get 11% of our patients were patients who arrived between midnight and 3:59 a.m. and had a positive alcohol screen. This will come in handy later. This also goes to the concept of independence. One variable is, testing whether one variable is independent of the other. This is an example of something that is not independent. So there is a dependence between time of day and alcohol results, clearly, as you can see that ranging from nearly 60% all the way down to about 10% here. So if we want to know if alcohol toxicology result is independent of patient arrival time, no, it's not. The rule for this is if the probability of A given B, probability of alcohol given time, is equal to the probability of alcohol or probability of A, or if the reverse is true, probability of B given A is equal to probability of B. Here's an example that does appear to be independent. The percent of our patients who are female, based on the admission day of week, you can see that doesn't vary a whole lot. The overall total percentage is 29.6%, and we see that ranging from 27 up to 31.9%. So not a whole lot of range there. And I actually added these error bars here. That's the 95% confidence interval, and we'll talk at a later date about what that really means. But just quickly, the 95% confidence interval is a range of values that you have 95% confidence that the true percentage is there. So if we were to repeat our observations 100 times, 95 of those observations would be in this range. And you can see a whole lot of overlap between all those confidence intervals there. Okay, another important concept that really relates to healthcare, and what we're doing is the concepts of sensitivity and specificity. This comes to play with when we're looking at screening tests, and we want to know how good a job they do. So sensitivity is known as the true positive fraction. So that's a number of results that are positive and really should be, divided by the total number of people who actually have that outcome, have the disease. So proportion of probability of having a positive test divided by the number of people who actually have the disease. Specificity is the ability of the test to detect people who really don't have the disease. And so that's the proportion of people who don't have the disease who have a negative test. False negative and false positive fractions are just the reverse of those. So this was an actual study that was done by Ingman and his colleagues, looking at the accuracy of ultrasounds performed by physicians in the emergency room in detecting intraperitoneal fluid in blunt abdominal trauma patients. And so they would just have the physicians perform essentially a fast in the emergency department, looking for free fluid, and with each of these 97 patients that they looked at, they also did a confirmatory test, either a CT or a DPL or a laparotomy, to look for fluid. And here are the results they found. So the physicians had positive results in 21 of these 97, negative in 76, and 24 of them actually had positive confirmatory tests. 73 of them did not. What we want to know is what's the sensitivity and specificity of the physician-performed ultrasound. And to do that, well, to do the sensitivity, we need to know the number of people who actually had fluid based on the confirmatory test, and divide and find out what proportion of those actually had a positive physician ultrasound. So the sensitivity is the probability of having a positive test given that you actually have the disease. It's 18 divided by 24 in this case, so we have a sensitivity of 75%. Can debate whether that's good or not. Specificity, again, is the probability of testing negative given that you really don't have the disease. So in this case, that's going to be the 70 true negatives divided by the 73 that had no fluid on that confirmatory test. So sensitivity and specificity are good for establishing the accuracy of a screening test and how good it is. But from the consumer's perspective, from the guy who's actually having the test done, you might care more about, okay, I just tested positive. What does that actually mean? And so what's the probability that I actually have the disease? So that's where we have positive and negative predictive value. Positive predictive value says, okay, you tested positive, here's the probability that you actually do have the disease. And that's going to depend on the sensitivity of the test and the specificity of the test, but also on the prevalence of the disease. So if it's a very rare disease, positive predictive value is going to be lower just because there are fewer people with the disease out there. If it's more common, positive predictive value is going to be higher. And so using that same example, we had 21 positive results. 18 of those actually had a positive confirmatory test, so they actually did have the disease, essentially. So their positive predictive value ended up being 85.7%. So that works out pretty well. Same deal with negative predictive value. Out of those who tested negative, 76, how many of them really were truly negative? And that's 70, so 70 divided by 76 is 92.1%. I swore I was not going to spend a lot of time on equations. So the idea behind Bayes' theorem here is just that you can calculate the positive predictive value or the sensitivity if you have enough other information about the test. So if you happen to know the sensitivity of the test and the prevalence of the disease and the proportion of tests that are positive, then you can calculate the positive predictive value. So example here is we've got a doctor who wants to screen patients for a disease. The disease prevalence is pretty rare, 0.2%. The sensitivity is pretty good, 85%. So 85% of the people who actually have the disease have a positive test, and 8% of his screens actually have a positive test. So that's the proportion, the P of B, and 92% are negative. So we want to know what's the likelihood of having the disease if that's a positive test. Another word for that is positive predictive value. So we can plug all that information into our equation based on Bayes' theorem. So prevalence of disease is 0.002. That goes for the prevalence of disease. Probability of testing positive, given that you actually have the disease, that's sensitivity. So we're just going to multiply the sensitivity by the prevalence and divide that by the proportion of tests that are positive. And that gives us a 2.1% positive predictive value. So you can see with a more of a rare disease like this, where only 0.2% of patients actually have the disease, the positive predictive value goes way down, which would make sense. Fewer people have it, it's less likely that you have it. Kind of sounds like circular logic. Okay. But I said I was going to talk about distributions, and so I am. The binomial distribution is probably one of the most popular. Binomial distribution is when you have two possible outcomes, heads or tails, success or failure, yes or no. So, of course, it is a discrete outcome, and each of the other properties are that each of the replications of the process are independent of any of the other replications. So the probability of success is the same each time you do it. And there's some important notation here. N is the number of times the process is replicated. P is the probability of success, and X is the number of successes that you're interested in. And once again, I swore I was not going to do a whole lot of equations. And this one is very scary looking. We'll go into what that means. Essentially, there are two components to this equation. One is the number of ways that you can get that number of successes. So that's the number of combinations. And the second part is the probability for each of those possible ways. So the Lakers just acquired a new center, Dwight Howard. He's a very good defender, good post player, but a bad free throw shooter. He makes about 40% of his free throws. Let's say the Lakers are up by 2 with 10 seconds left in the game, and he gets hacked because the opponent knows that he's a bad free throw shooter. And so it's really important that he makes at least one of these free throws, because the opponent has a really good three-point shooter. So we want to know, and we're taking, well, making a friendly wager towards the end of this game, based on how likely it is he's going to make at least one of these shots and hopefully ice the game, or at least not lose it in regulation. Since he is a 40% free throw shooter, we know the probability of him making each shot is 0.4, 40%. But we want to know, okay, they're in the double bonus. He's got 2 chances. What's the probability he's going to make at least one of those? There are 4 possible outcomes here. He can make both of them. He can make the first one and miss the second one. He can miss the first one and make the second one. Or he can miss them both. Anytime for each make, that's a probability of 0.4. So if he makes them both, that probability ends up being 0.4 times 0.4 for a probability of that happening of 0.16, 16% chance that he makes both shots. If more likely he's going to make one and miss the other, so if he makes the first one and misses the second one, the probability of making the first one is 0.4, missing the second one is 0.6. Multiply those together, probability of that happening is 0.24. Same deal with outcome 3, where he misses the first one and makes the second one. That probability is also 0.24. And the most likely of all is that he misses them both. But fortunately, that's only 36% of the time. So, what's the probability he's going to make at least one of them? Well, the probability he makes both of them, again, as I said, was 16%. Probability he makes one of them, we don't care what order he makes them in, is going to be 48%. So the probability he's going to make at least one of those free throws is just adding all those up together, 0.16 plus 0.24 plus 0.24. So we've got a 64% chance he's going to make at least one of those. So we've got at least a 3-point lead. And as long as we don't foul the 3-point shooter, we're not going to lose the game in regulation. All right. And this is the, so I mentioned the number of possible combinations of ways that you can get an outcome. This is actually the equation for that. This is not pronounced n, it's pronounced n factorial. And that just means that you multiply the n, so if instead of n you're saying 5, that is calculated as 5 times 4 times 3 times 2 times 1. It's just multiplying sequentially down until you get to 1. Obviously, we have computer programs to do all this, and you can calculate the number of combinations on a basic scientific calculator using this n choose x or maybe n choose r button on your calculator. So that's the first part, is finding the number of combinations of ways that outcome can happen. The second part is finding the probability of that number of successes in a number of specified trials. And that's just the probability of success multiplied x times for that number of successes times the probability of failure, 1 minus p, times the number of times that failure happens, or multiplied by that many times. So to use a more health-related example, we've got a medication for allergies that's effective in reducing symptoms 80% of the time. So that's going to be that p equals 0.8. If the medication is given to 10 patients, we want to know the probability it's effective in exactly 7. So again, the probability of 7 successes, here's the number of combinations of ways, and that's the probability of each of those outcomes. And yep, number of combinations with 7 successes out of 10 trials, and the probability for each of those combinations. So there's 120 different ways that you can get 7 successes out of 10 trials, and this other part is the probability for each of those outcomes. So the probability of 7 successes ends up being 0.2013. We can extend that, so if we want to know at least 7, then we just need to repeat that for 7 and 8 and 9 and 10, add those all together. and that gives us the probability that it's going to be successful in at least seven times. Now, if we look at the binomial distribution, actually has a pretty characteristic shape. Actually, it looks a lot like the normal distribution when you start to calculate all of the possibilities. So there's each of these outcomes has a measurable probability of happening, and you can see it rising up to a peak at 8 and going back down. Obviously, there's not a very long tail here because we only have 10 possible outcomes. Okay. If we were to increase the number of trials to 100, we get a much smoother curve here, and it looks a lot more like a normal distribution. And we can use some of the properties of the normal distribution instead of that unwieldy equation to measure some of the probabilities of the binomial distribution. So, other things you need to know about the binomial distribution. We can essentially refer to the mean of the binomial distribution as the number of trials times the probability of success, so n times p. In our example before, if we were repeating the process 10 times, that would be n, and the probability of success is 0.8, then the mean or the expected number of successes would be 0.8 times 10, or 8. The variance, maybe not quite as intuitive, is calculated as n, again the number of trials, times the probability of success, times the probability of failure. So n times p times, we usually use q to refer to 1 minus p. And so the standard deviation, again, is just the square root of the variance, or the square root of n times p times q. All right, so that's the binomial distribution. The normal distribution is the model for a continuous outcome. There, with many continuous variables, we assume that they are distributed in a normal fashion, and by that we mean this bell curve shape. It's also known as the Gaussian distribution, and there are some other names for it. But it has a couple of properties here. The mean is right here in the middle, so it happens to be equal to the mode and the median. Also, on our standard normal distribution, we call that mean 0, and then we measure in terms of fractions or units of standard deviations away from the mean. So we have a score that's called the z-score, and what the z-score represents is the number of standard deviations away from the mean that it is. The other properties is that about 2/3 of observations are going to be within 1 standard deviation. About 95% of properties are within 2 standard deviations of the mean. This is an example just from our registry. Looking at systolic blood pressure, you can see it doesn't look quite as pretty as the smooth curve, but you can see we would say that it approximates a normal distribution because it's pretty close. Our mean here is 137 millimeters of mercury and standard deviation of 24. So it sounds like our patients have kind of high blood pressure. Again, our notation is going to be that mu is the mean, sigma is the standard deviation. And this kind of repeats that. So, if we want to know, well, let's say we have that we know that body mass index for men in a certain age group, 60, is normally distributed. The mean is 29, standard deviation is 6. We want to know what the probability that just some randomly selected guy who's 60 years of age has a body mass index less than 35. For some reason, we've got a study that's where we need to have men who are not more than 35 in their BMI. So, since this is how that's distributed, we know 35 is above the mean. What we need to do first is convert our units, convert our units of body mass index to a z-score. So it fits with what we saw before, where the mean is 0 and standard deviation is 1. So in order to do that, we take that observation, in this case 35, subtract off the mean of 29, and divide by the standard deviation. And so that's going to convert it to a standard normal distribution with mean 0, standard deviation of 1. So since that equation is going to give us a result of 1, 35 minus 29 is 6, divided by 6 is 1. What we want to know is the probability that z is less than 1. Okay, in almost any statistics text, you have a table in the back of the book. These are all derived from some equation that shows you the area underneath the normal distribution curve to the left of the value that you're interested in. And it's, I'm sure, kind of hard to see all these little numbers. but it gives, again, the area under the curve, which can also be interpreted as the probability of an observation happening less than that value. So you can see here at 0, the way to read this is you look at the margins. So 0.00 is going to be the mean. And so the value there is 0.5, meaning half of the observations are less than that, which we know. and that goes up. So for a probability for a z of less than 1, so here's 1.00, and that probability is 0.8413, meaning 84.13% of observations are going to be less than one standard deviation above the mean. And so this is a way to think about that. It's all right, so we're talking about this much of the area under the curve. And I kind of just went through all that. So basically what we're going to do is just find that value for a z of 1. That gives us 84.13%. We can also find the expected percentiles if we have a distribution that is normally distributed based on those z values, just like we had before. Of course, the median is the 50th percentile, so that would be a z of 0. First quartile is a 25th percentile. Third quartile is a 75th percentile. And those are determined by, and we can reverse calculate to find the actual value of that distribution, say body mass index or whatever it is we're interested in, to determine the percentile of that distribution. So here are the z values for certain percentiles. We might be interested in the 95th percentile, for instance, where the z value there would be 1.645, or the 90th percentile, if you want to know the top 10%. And so we know that, again, that BMI in men follows that normal distribution, mean 29, standard deviation is 6. And in women, it's a normal distribution with a mean 28, standard deviation is 7. And so that 90th percentile for men is going to be, again, that mean plus the z value for that 90th percentile times the standard deviation. So the 90th percentile is going to be 36.69. You can calculate it the same way for women, mean plus that z value times the standard deviation. So, and it's actually remarkably close between the two of them. Okay, the central limit theorem. This is really useful because not all distributions follow a normal distribution. They don't all obey that bell curve. Things like length of stay in the hospital or ISS are good examples of that. So, but if we have a population with a known mean and standard deviation, sigma, then we can take, this is assuming we just take random samples of a consistent size, and then as long as those are big enough, and by big enough we usually mean about 30, the sampling distribution of the means is going to follow a normal distribution. The only different thing about this is that instead of using our sigma for the standard deviation, we're going to take that sample size into account. And so, we're going to calculate what's called a standard error. And the standard error is calculated as the standard deviation divided by the square root of the sample size. Otherwise, it's exactly the same as what we just did. Again, we're going to apply this to non-normally distributed populations, and again, we're going to find that the distribution of the sample means it approximately follows a normal distribution. So you can use that z to compute probabilities, where before we were subtracting off the population mean and dividing by the standard deviation. Now we're just dividing by the standard error. So the standard error being the standard deviation divided by the square root of the sample size to find the z-value. That's when we're dealing with samples. So our example here, HDL cholesterol has mean 54, standard deviation 17. In this age group of patients, physician has 40 patients, so N is going to be 40, who are over the age of 50, and he wants to know the probability that the mean value for that sample is above 60. So probability that X bar is over 60 is, well, again, we do just like we did before. We need to convert this to a z-value, so we subtract off the sample mean, or subtract off the population mean from the sample mean, and divide by that standard error. So that the standard deviation is 17 divided by the square root of the sample size, which is 40, gives us a z-value of 2.22. So that's 2.22 standard deviations above the mean that you would expect. And so the probability of finding that, so this is that value from that table we would get. So 98% of observations are going to be less than that. Since we want to know the probability that it's greater than that, we're going to take 1 minus that value from that table and find that only about 1.32% of the time we're going to expect to have a sample that is that large, or that has HDL cholesterol that high. All right. So in summary, probability is just the likelihood an event is going to occur. It ranges from 0 to 1. 0, it's not going to happen. 1 it's absolutely inevitable. It will happen. If we have mutually exclusive events, that means that if one happens, the other one won't. And we can use the additive rule when we want to know if one or the other is going to happen. Conditionally dependent, that's the multiplicative rule, where if you want to know if both are going to happen, that's just the probability of one happening times the conditional probability of the other happening. We went over sensitivity and specificity and positive and negative predictive value, as well as the binomial distribution. That's just the number of possible combinations of ways something can happen times the probability of each of those combinations happening. And when it's large enough, that binomial distribution can approximate the normal distribution. So you can use a lot of the properties of the normal distribution to evaluate that, even if you only have 2 outcomes. Normal distribution, again, has some characteristics all its own. The mean equals the median and the mode. And z is probably the most important thing to remember here. Z is just the number of standard deviations away from the mean. Remember that 95% of our population of our observations are going to be within 2 standard deviations of the mean. So that's why a lot of the times we'll use 2 standard deviations as a rough estimate of significance. And central limit theorem is useful when evaluating the distribution of sample means, because the sample means are going to approximate the normal distribution, even if the raw distribution is skewed. All right, so we're done for this morning. Next time we're going to talk a bit about hypothesis testing and statistical inference. When you're looking at peer-reviewed journals, often you will see p-values and possibly confidence intervals, sometimes in the same spot. We'll talk a little bit about how to interpret those, and how to know what tests are appropriate to use in what situations, depending on what kind of variables you have. Any questions?